Okay, so now we want to talk about the different categories of data mining problems and output patterns, and we've seen some of this already, uh, and we talked about it in class, but let's go over it again. Um, so we're going to sort of categorize the different problems that we do in terms of, basically in terms of the end result that we're looking for, or the type of end result that we get. So we do, in data mining, we do what's called classification, and that's when the output is categorical. So if you're trying to decide, trying to predict which soda that someone will like, sodas are like, you could have Coke, Pepsi, and Sprite, and some other ones. So those are classes or categories. So you're trying to put someone into a class or a category. If you're trying to predict whether someone has a disease or not, that's also a category. Two things. Either they have it or they don't. If you're trying to predict whether something is an iris, what is it? What was it? A setosa, an iris virginica, or a iris versicolor, those are three different outputs, three different categories rather, that they can be in. And so that's again, the output is categorical. On the other hand, if you're trying to predict the temperature tomorrow, really we think of temperature as being like on a continuous, kind of continuous spectrum. So the temperature could be 22 degrees, it could be 22.1 degrees, it could be 22.11 degrees, it could be 22.111 degrees, right? So in that case, we don't think of the output as being categorical. We say it's continuous. And in that case, we call the problem estimation. And then we have something called cluster detection, which I'll show you a little bit about shortly. And then something called association mining, which is sort of like the first case, the classification, but when we don't have a particular output variable that we're trying to use. So I'll explain that a little more carefully later, but for example, we might have, for example, in the weather problem, where we're trying to weather and golf problem, where we were trying to predict whether people were going to play or not. I think we had four other variables, but we are always focusing on predicting the play versus not play variable. But if we weren't specifically focusing on predicting one of the variables and just were looking for rules that would predict any particular variable, so it might come up with a rule that predicts what the temperature is based on the other variables. So if you're not focusing on one particular output variable, we call that association mining. Okay? So let's look at these a little more carefully, each one of these, and then we're gonna sort of do that broadly here, and then we're gonna spend one lecture on, say, just one of these as we go on in the class. But right now, let's look at all of them quickly. So here's the weather problem again, or it's the golf problem again. So we have our example data set. So this is for classification. So we have the variables outlook, temperature, humidity, windy, and class. This is play versus not play. And we will go through we'll choose a model building method, and then we'll actually do the classification using that method. And then we'll take a new record. For example, we'll say, suppose it's sunny, cool, high, and true. So that is these four variables. These four variables have those values. Then we put that into our classification model, and it will predict something for us, like that they won't play. And we will call this down here the unseen data record. And maybe a more practical example of this would be of a classification problem would be to build a model to predict whether an application for a credit card should be accepted or rejected. So again, we'd still have two classes that we were trying to predict. So we talk about the instance space, and let's see. The instance space is a multi-dimensional space defined by descriptive feature variables. So what is that? Well, that just means this. So this is called the instance space here. This whole thing here. Not out here, just this. And so the instance space here consists of, actually I'm not sure if they mean by the instance space it includes this variable or not, but anyway, outlook, temperature, humidity, windy, and maybe this variable as well. That's called the instance space. This is just the set of variables that we're considering. So they call it a space because if you only had two variables, like just outlook and temperature, you could call one x and the other y, and you could draw a graph, right? Just a simple xy graph. And so that's kind of a space. And then if you had three variables, you could still draw a graph, right? You could have x, y, and z, so you could draw a three-dimensional graph, and that's still kind of a space. So even if we have more than that, where we obviously can't draw it, but still we can talk about it as a kind of a space. So it's called the instance space. The instance space is a multi-dimensional, so it could be one-dimensional, could be two-dimensional, could be three-dimensional, but it could be more. Space defined by descriptive feature variables. So I guess these are called descriptive feature variables, or they're just variables. Training examples are considered to be points in the instance space. Yeah, well, let's go back to this again. Suppose we only had these two variables. Suppose we didn't have any of this. And maybe we have the class, but just these two first, just outlook and temperature. So we could call one x and one y, and then you know, if it's a little clearer if you think of it numerically instead of, so outlook is really not a numerical variable. Temperature could be numerical. Let's suppose instead of outlook, temperature, let's suppose we had temperature and humidity. So we'd have an x-axis maybe is temperature and a y-axis which is humidity. For example, suppose we had this. So then a point which is out, say here, would have high temperature and low humidity. A point here would have low temperature and high humidity. And let's assume that these are numerically measured, not categorically measured. So temperature is actually a number. Humidity is actually a number, like temperature might be 30 degrees and humidity might be 80%. Something like that. So if you had something that was like 30 degrees and 10% humidity, that would be over here. If you had something like maybe 10 degrees and 90% humidity, that would be over here. So these are just, we say these are points. So if you have a point over here, that's a point in the instance space. Because if I'm saying this, suppose the instance space only consisted of these two variables, not all of the variables that we were talking about before. So a point here is a point in the instance space. And if you had three dimensions, you'd have a point in the instance space as well. And so we talk about just, it doesn't matter how many dimensions we have, we're still going to call it a point in the instance space. So training examples are considered to be points in the instance space. And also we may later choose to weight some of the variables more and some less before we enter them into an algorithm. And here's an example of what's called the nearest neighbor algorithm. So like you have an x-axis and a y-axis, and you have so-called training examples. Not, in other words, remember here we talk about the unseen data record. But first we have the training examples. These are called the training examples here. So first we have those. So suppose we had training examples, and suppose we only have two variables like temperature and humidity. So that's what I'm trying to picture. That's what I'm picturing here. Only two variables. So suppose we only have two variables, and we have a bunch of data for just those two variables. So temperature and humidity. Maybe there was a case where it was hot. We're using temperature. We're using numbers. So suppose it was like 30 degrees and 80% humidity, and 30 degrees and 75% humidity, and so on. We had data like that. That will be called our training data. And with each of those examples, so this first one, and this second one, and this third one, with each of those we're going to have the class. So the class is going to be, in this case, N or P, but it could be anything, and it doesn't just have to be limited to just two possibilities. It could be 3 possibilities or 4 possibilities or whatever. Alright, so that's what this picture is about. So here I'm just supposing that we have just two variables, like the x-axis and the y-axis. Here I said, for example, suppose that not humidity and temperature, but say education level and income level. Just another example. So, over here would something over here, for example, this one would be high education level and also high income level. But something like this one over here would be low education but high income, and so on. So each of these points represents some combination of education level and income level, and each of these points we're thinking of them as points in our instance space, right? Or I'm sorry, what did we call it? What did I just call it? Our training data, I guess we'll call it. So this is our training data, and so we have color here, blue and red, and actually green, but we ignore the green for the moment. We have blue and red, so that might, let's say that blue indicates a bad candidate for a loan, and a red indicates a good candidate for a loan. So this means that we had a person in the past whose education level was very low, but whose income level was quite high, and they ended up defaulting on their loan. So this is a past example. And this one over here is someone whose education level was very low, but their income level was kind of average, in the middle, right? It's sort of in the middle of this height, in terms of height. And they also turned out to be they also defaulted on their loan. They turned out to be a bad candidate for a loan. Okay, on the other hand, we have someone over here, let's say red means that they were good. So here we have someone who was, so I'm saying that blue meant that they were a bad candidate, and let's say that red means that they're a good candidate. So here we have an example of, in the instance space, or in our training data, of someone who has a high education level and a high income level, and they, in the past, turned out to be a good prospect for a loan. They paid back their loan. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blues and reds. So those are our past data. Now we have a new person represented by the green, and we don't know, they're like a new person. We don't know whether they're going to pay back their loan or not. We're wondering about it, and we're wondering should we give them the loan? How should we classify them, as a good candidate or a bad candidate? So the idea of the nearest neighbor is we look at a neighborhood around this green person. So this green person, by the way, is what? They have a kind of medium education level and a medium income level. So we draw a circle around this green dot, and the radius of the circle is, you know, sort of up to us. So we draw, say, this circle around it, and then we look at the neighborhood. That defines like a neighborhood around the around the green dot. So then within that neighborhood we say, well, what's sort of the nearest neighbor? And this, and this as the sort of the nearest neighbors. And so then that can sort of help us decide how should we classify this green one. So maybe because there's more red in here and they also are actually closer, although I'm not sure we consider that. We just say how many are in the circle, period. So then we'll say within that circle there are 2 red and 1 blue, so maybe we should classify it as red, or that they will be a good candidate. Okay, and that's the idea of the nearest neighbor. We could draw a bigger circle, and then we have this one, this one, this one, this one, this one. Then we might say, well, actually, we're going to classify them as a bad because it's 3 to 2. So depending on the radius of the neighborhood, you might get different answers. Now, the problem here is that education level is like, what, 1 through 20, and income is like 0 through, you know, 50 million or something like that. So we might have to kind of weight education level higher, because just as a number, it's going to be tiny compared to income level. So we might have to do something like that. And that's what I said when I said this. We may choose to weight some of the variables more and some less before we enter them into an algorithm. So that's one reason why we might do that. Okay, so this is the idea of the nearest neighbor. So to review this, to classify a new object, an unseen data record, we may compute the distance between the new object and each element in our instance space, our data set, and the nearest or k nearest neighbors of the object are located. So here it's slightly different actually. I said choose a radius, but what this is saying, what I just said just now, is that what we could do is look at the distance between this one and this one and this one and this one, and look at the distance of this green from all of the points, and then just look at the closest 3 or the closest 4. So we don't actually draw a circle. We just say, okay, I'm going to look at the closest 4. So what are the closest 4? This one, this one, this one, and this one. So if I look at the closest 4, it's kind of 50-50, right? There's 2 blue and 2 red, so I wouldn't really know which one to classify it as. If I look at the closest 3, then it's 2 to 1, so maybe I would classify it as red or as a good candidate. Okay, and so on. So if you could do it that way as well. And the nearest, you could just use the nearest one. So since this is the nearest one, I'll classify it as red. That's one option. Or you could say I'll use the 2 nearest. In that case, the 2 nearest are, I guess, these 2. So you'd still classify it as red. Or you could say I'll use the 3 nearest. Then you would still probably classify it as red. If you use the 4 nearest or the 5 nearest, then you'd probably classify it as blue. So you could change that parameter and you'd get different answers. So, and the nearest or k nearest neighbors of the object are located. The class of the object is then decided by the class of its nearest neighbor or k nearest neighbors.